Hello, my name's Yasmin, and today I'll be talking to you about sound waves and plants. I'll be walking you through a couple of definitions with regards to sound waves and different concepts. I'll be talking about the effect of sound waves on plants, plant communication, and also current research going into bioacoustics with regards to plants. And finally, my references. So here are a couple of definitions that are very important to understand before going through the effect on plants. So what is a sound wave? Well, it is a mechanical wave, which means it has air particles vibrate and also displace and move because of the sound. It is equally longitudinal, meaning they are I waves and that are parallel to the source of sound. So, as we can see here with the pitchfork, um, the sound waves are coming out and moving parallelly. And when they are very condensed, that means it's the end of one wavelength of the frequency and repeated, so pulsated. Amplitude is another very important concept. Amplitude is the volume measure. So as the amplitude is bigger, you'll be hearing sound more loudly. If it's smaller, not as much as in the figure here. And finally, frequencies. We'll be looking at acoustic frequencies, which are in the 20 hertz to 20 kilohertz range. And we'll be explaining that lower frequencies have longer wavelengths and higher frequencies have smaller wavelengths. What is the effect on plants? Well, sound exposure experiments happened with fixed frequencies or alternating frequencies. For fixed frequencies, that's only when they have the plant subject to one frequency. In fixed alternating frequencies, they'll have songs playing typically classical music or predetermined set range of frequencies. Typically, the plant will be exposed to the sound for a set amount of time per day, so 6 to 8 hours typically. So, as per an experiment that was conducted by Kim and Jo Yu in 2015, we can see that the ripening of tomato plants was different for plants that were subject to 1 kilohertz and plants that weren't subject to any noise or the actual random noise that happens in everyday today life. So you can see after the 14-day period, the 1 kilohertz did have an effect and the ripening was much slower. It started looking pretty much similar at day 12, but the tomato stayed overall green throughout the experiment. Other biological processes that can be regulated with sound are the transpiration rate or growth rate. However, this is plant specific. It doesn't mean that there will be a positive outcome every time. Sometimes it may be not so beneficial. Another experiment that was conducted was on inpatients. As we can see here on the graph, we have height as a function of time, and we can see a dramatic difference in height for the control plant and the plant that has been exposed to 14,000 hertz. Even random noise had a better effect. Again, we have to remember that the plants have to have a short growth period, which was 28 days in this case. But again, that doesn't mean that every plant will have a positive outcome, being subject to all types of frequencies. Another important aspect is plant communication. Plants do emit noises. Sometimes they weren't in the acoustic range. However, the most noticeable ones were with pollinators. So they do signal the pollinator to come and release pollen. The stomata opening also has a very low frequency release, and cavitation during drought. So these are related because it is releasing water or losing water content. For droughts, they are not just signaling also surrounding plants, they are also signaling biodiversity to say lack of water. So the current research that is happening now with regards to bioacoustics is trying to better understand plants and how they emit noises. Right now, the research is very limited, so it's very hard and they don't know what kind of direction to go into. So on the picture on the left here, we have hydraulic sensors that are attached to leaves. So they're trying to see the displacement of water when there's sound. And sometimes they're trying to relate that with piezoelectric, meaning once someone touches it, if they release sounds and trying to create a bond uh, between the user and the plant. And on your right is a picture of someone from the University of Cambridge that is part of the Plant Orchestra project. So they're trying to better understand plants, and here they're doing it with aquatic plants. The type of microphones they're working with are very, very sensitive, and also trying to do this through different mediums, so not only air, but water as well. So far, the results yielded are not that spectacular, but it is ongoing research. Here are my references, and I'd like to thank Mark Lesford, Dumont, and Ngadi, and my reviewers. Do you have any